episode, this is also same type of frame, but differently loaded. This frame contains a pointed load at point C of 2 kilonewton and the uniformly distributed load of 12 kilonewton per meter together. I want to deal with it to show how it is done. The reaction, of course, is the totality of the load. The UDL, totality of it will be 12. Reaction at A is the totality, 12 times 5, then plus 2, which is equal to 62 kilonewtons. That's the reaction. 12 times 5 is 60 plus 2, 62 kilonewtons. That's the reaction at A. Now, to get the bending moment, let's say moment at C is equal to 0. Moment at C is equal to 0. You must have known, if you are following this lecture, you would have known why moment at C is 0. Because there's no distance of C from itself. The moment at C is 0. And there's no support for that matter. Then we now move. Then at point E, which is half of the distance, 2.5 meters. That's the M at E, is equal to minus 2 times the distance, 2.5, that's the perpendicular distance. Then minus 12 times 2.5 squared over 2. That's 2. From E to C. E to C, 2.5 times 12 as a bunch of load, then times half of the distance, because we're taking moment at E. That's why it gave this. That is, this is equal to 5 to minus 5 minus 6 times 2.5 squared. At point B, M at B, moment at B, is equal to minus 2 times 5 minus 12 times 5 squared over 2, which is equal to 2 times minus 2 times 5 is minus 10. Minus 2 times 5 is minus 10. Minus 197.5 kilonewton meter. So minus 2 times 5 minus 10, then minus 25 times 6. You have minus 197.5 kilonewtons. That's the moment at B. Each of them created a moment. The first two created a moment by multiplying the distance of 5 to create a moment. Force times perpendicular distance. The force, 12 kilonewton, multiplied by 5 gives you the bunch of the load, the complete load, total load. Then half of 5. That's why you have 12 times 5 over 2. So you have 12 times 5 squared over 2. So at M at F, the moment is concentrated. If you've been following the other episode, the moment is concentrated. It becomes still minus 197.5 kilonewton meter, because the length BF is not perpendicular to any of the loads. It is parallel to the line of action of the loads. So the moment is concentrated. Now, M at A is still equal to minus 197.5 kilonewton meter. So that is that. That is the bending moment. We will now draw the bending moment diagram. Draw the bending moment diagram. So if I draw the bending moment diagram, we have something like this. At point C, moment is 0. And you see the equation of moment at point E up to B is quadratic. It's quadratic, and as such, the graph will be a curve. It's a quadratic function. The graph is a curve. Negative. That's 197.5 kilonewton meter. So that's at point B. At point B, this C. So now in BA, the line BA, it was the same thing. So that's why it became a rectangle of equal width. That width is 197.5 kilonewton meter. Negative. This is the bending moment diagram. Bending moment diagram for this frame. So shear force at C, the shear force is minus 2 kilonewton, minus 2 kilonewton. That's shear force at C. The shear force at B is minus 2 kilonewton minus 12 times 5, which is equal to minus 62 kilonewton at B. So, and it was varying. At C is minus 2. So the bending moment diagram, the shear force diagram, minus 2. Sorry, minus 2. It increases. It starts increasing till, look at it, till increase this to minus, this is 2. This is 62. There is no shear force in BA. But there's one normal force there. The normal force along BA is 12 times 5 plus 2. That is 62. Shear force diagram. Normal force diagram. 62. 2 kilonewton. So that's that. Both shear force, normal force, bending moment has been calculated. So the beam has been analyzed and the diagram drawn. Thank you very much.